we are going to discuss about the contamination particles based on the conditional rule. And on inspection of a large number of semiconductor wafers revealed the data for this table here. And the wafer is selected randomly. And the left column indicates the number of contamination particles, and the right column indicates the proportion of wafers. So the proportion of wafers, including 0 contamination particle, equals to 0.4. And the proportion of wafers, including 1 contamination particle, is 0.2. Okay? So the proportion of wafers, including 5 or more particles, equals to 0.1. So the total summation of the proportions will be 1 here. And in this case, what is the probability that it contains no particles? And the proportion of the wafer, including no contamination particle, is 0.4. So 0.4 divided by the total proportion 1 will be the proportion of that it contains no particles, right? So that equals to 0.4 or and what is the probability that it contains 3 or more particles? Firstly, we have to calculate the proportions of wafers, including 3 or more contamination particles, right? So proportion of wafers, including 3 or more contamination particles, will be the summation of 0.1, 0.05, and 0.1, right? So the proportions of the wafers, including 3 or more contamination particles, will be 0.1 plus 0.05 plus 0.1. So we have to calculate the probability. So we have to divide this summation by the total proportions. So that equals to 0.25 or 25%. And that is the probability that it contains 3 or more particles. And this is another example. And this is the case of sampling without replacement. And a batch of parts contains 6 parts, such as A, B, C, D, E, F. In this case, 2 parts are selected randomly. And suppose that part F is defective and order is not important. In this case, what is the probability that part F appears in the sample? As shown in this example, order is not important. So we can apply the conditional rule rather than the permutation rule. So to calculate the probability, we have to first calculate the total number of possible samples. And as I mentioned previously, we can apply the conditional rule. And what is the total number of samples in a set? That is 6, right? And the number of samples in a subset, that is 2. So there will be C of 6 and 2. That equals to 6 factorial divided by 2 factorial multiplied by 6 minus 2 factorials. And there will be 6 multiplied by 5 multiplied by 4 factorials divided by 2 multiplied by 1 multiplied by 4 factorials. Okay? So the 4 factorials can be eliminated each other, and 2 can be eliminated by dividing 6 by 2, and there will be 3. So the total number will be 15. And what is the number of samples that contain part F? In this question, the order is not important, right? So this will be A, F, B, F, C, D, F, and E, F, right? And as shown in here, there is no replacement, and there will be no FF. So the number of samples that contain part F will be 5. So what is the probability to contain part F? That will be 5 divided by 15, right? And that is 1 divided by 3, or 33.3%. So that is the answer for this question. This is the probability that part F appears in the sample. And now we are going to discuss about the axiom of probability. Probability should satisfy the following 3 properties. First one is that the probability of the sample space equals to 1. And the probability of some event should be between 0 and 1. And for 2 events, E1 and E2, with the intersection of E1 and E2 equals null set, the probability of the union of E1 and E2 should be equals to each probability. And these are the axiom of the probability. So from this definition, the following properties can be obtained. The probability of null set equals to 0. And the probability of the complement of E equals to 1 minus the probability of E. Why? When we use the Venn diagram here, this is the sample space, and we can say this is the event E. The complement of event E will be this part, right? So the probability of the complement of E equals to the probability of the sample space minus the probability of E, right? But as you can see here, based on the axiom of the probability of the sample space equals to 1. So this can be rewritten as 1 minus probability of E. So the probability of the complement of E equals to 1 minus the probability of E. And also, if E1 is contained in E2, then the probability of E1 should be smaller than the probability of E2. And this is about the addition rule, which is called 가산규칙 in Korean. The joint probabilities are generated by applying basic set operations to individual events as follows. And we all know about these 3 properties. First one is the union of events, and this can be expressed by this relationship, A union B. And the intersection of events can be expressed by this equation, A intersection. Complement of event can be expressed by the A prime. And the probabilities of joint events can be determined from the probabilities of the individual events that comprise it. And this can be understood by the following example. And this is the example 2-19 for the semiconductor wrapper. A wrapper is selected randomly from a batch as shown in the table. And this is the table. We have 4 variables. Our first one is the low contamination, and the other one is the high contamination. And also, we have 2 locations. First one is the center, and the other one is H. Let H be the event of high concentrations of contamination. Then the probability of H will be 358 divided by the total number, right? Because in this case, we don't have to consider about the location. And let's see, be the event of the wrapper being located at the center of the tool, then the probability of C can be 626 divided by the total number. Because in this case, we don't have to consider about the contamination. In this case, what is the probability of the intersection of H and C? That is the question. In this case, we first have to calculate the number of intersections H and C, right? So the intersection of the H and C will be 112, right? So the probability of the intersection of H and C will be 112 divided by the total number, right? So this is the probability of the intersection of H and C. And what is the probability of the union of H and C? We can simply understood this based on the Venn diagram. This is the sample space, and this is the event H, and this is the event C. The union of event H and event C will be this shaded area, right? And this, for calculating this, we can separately add the event H and event C first, right? But in this case, the intersection is duplicated. So we have to subtract the probability of the intersection between H and C. Okay? So this is the equation to calculate the probability of the union of H and C. So based on this equation, what is the probability of H? That is 358 divided by 940 plus what is the probability of an event C? That is 626 divided by 940 minus the probability of the intersection of H and C will be 112 divided by 940. So there will be 358 plus 626 minus 112. So this is the probability of the union of H and C in this case. Okay? So the probability of a union can be expressed by this equation based on this concept. And if it is rearranged, the probability of the intersection of A and B can be equals to the summation of each probabilities minus the probability of the union of A and B. If event A and B are mutually exclusive, which is called 상호 배타적, in this case there is no intersection. So the probability of the intersection of A and B equals to null set. Therefore, this equation can be simply expressed by this equation. The probability of the union of A and B equals to each summation of each probability, A and B, because this equals to 0. And this is another example. In the previous example, are classified by the degree of contamination and location in the following table. And the left column indicates the number of contamination particles. And there is also the location parameter. And these are the proportions of vapors. So these are the questions. E1 is the event that a vapor has 4 or more particles. What is the probability of E1? So the first question is that we have to select the vapors including 4 or more particles. So the proportion of E1 will be 0.05 plus 0.1, right? So the proportion of E1 will be equals to 0.15. So the probability of E1 will be 0.15 divided by 1. That equals to 0.15 or 50%. And E2 is the event of a vapor was on edge. So the proportion of vapor which is located at edge is 0.28 here, right? Because in this case, we don't have to consider about the number of contamination particles. So the proportion of E will be 0.28. So the probability of E2 will be 0.28 divided by 1 equals to 0.28. Okay? Because E2 is the event that a vapor was on edge. So in this case, what is the probability of the intersection of E1 and E2? The proportion of E1, the proportion of the intersection of E1 and E2 will be these two, right? That is the intersection. So the proportion of the intersection of E1 and E2 equals to the summation of 0.01 and 0.03. That equals to 0.04. So the probability of the intersection of E1 and E2 will be 0.04 divided by 1 equals to 0.04. Okay? And what is the union of what is the probability of the union of E1 and E2? This can be calculated by this equation, right? So this will be 0.15 plus 0.28 minus 0.04. That equals to 0.39. So this is the probability of the union of E1 and E2. And now we are going to discuss about the addition rule for 3 or more events. A union of 3 events can be expressed by this equation. The probability of the union of A, B, and C equals to the summation of each probability minus the probability of the intersection of A and B, A and C, and B and C, plus the probability of the intersection of A, B, C. And this can be easily understood by the Venn diagram also. So when we have the summation of each probability, this part is duplicated, right? So we have to subtract each intersection, right? Here. But as you can see, we subtract each intersection this part is completely eliminated, right? So we have to add this part again. That is the probability of A, B, and C. Okay? So the probability of the union of A, B, C can be calculated based on this equation. And in the case of the mutually exclusive event, if a collection of event E1, EI is mutually exclusive, the intersection of EI and EJ equals to null set. So that means the probability of those intersections equals to 0. So the probability of the union of E1, E2, blah, 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 and EK equals to the summation of the probability of EI from I equals to 1 to K. So in the case of the mutually exclusive event, we can simply calculate the probability of the unions based on this simple summation. And this is the Venn diagram for the mutually exclusive event. And this is the sample space. And these are the events which are mutually exclusive. And as you can see, there is no intersection, right? And now we are going to discuss about the conditional probability. Sometimes probabilities should be reevaluated as additional information becomes available. And P, B dash A is called the probability of event B when the given event A has already occurred. This is called the conditional probability. And we can say the conditional probability of event B given an event A. This is the typical example. A communication channel has an error rate of 1 per 1,000 bits transmitted, and errors are rare but tend to occur in bursts. This means that if a bit is in error, the probability that the next bit is also in error may be greater than 1 divided by 1,000. So the later event is obviously influenced by the previous event, which is the first error, right? So in this case, we can calculate the probability based on the conditional probability concept, because the previous event influences the next event. And this is another example. In a thin film manufacturing process, the proportion of parts that are not acceptable is 2%. However, the process is sensitive to contamination that can increase the rate of part rejected. So in this case, the contamination obviously influences the part which will be rejected, right? Influenced by previous event. So this is also can be solved by the conditional probability concept. Okay? And this is the examples for the conditional probability. In a manufacturing process, 10% of the parts contain visual surface flows, and among them, 25% are defective parts. In contrast, only 5% of parts without surface flows are defective parts. So let D denote the event that a part is defective. Let F denote the event that a part has a surface flow. So in this case, the probability of D, given that a part has a surface flow as that is the conditional probability, right? Because the probability of D is influenced by the previous event, which is that a part has a surface flow. So we can calculate the probability of D based on this conditional probability equation. So the conditional probability of D given F will be 25%, right? Why? Because there are 25% of defective part among 10% of the part contain visual surface flows. 그러니까 저희가 이 25개를 선정할 수 있다는 것은 이미 visual surface flow가 있는 상태에서 뽑을 수 있는 거죠. 그러니까 conditional probability예요. 아시겠죠? And what is the probability of D given that a part has no surface flow, which is called F prime here, will be the conditional probability of D given the complement of event F. And this will be 5%. And this is the simple example for the conditional probability. And so we can simply express these two things in the Venn diagram. This is the sample space, okay? And this is the event F. Indicates parts with surface flows. Right? And this is the complement of F, that is part without surface flows. So in this case, we have 25% defective part here, right? So this will be the conditional probability of D given F. There will be 25% here, okay? And this part will be the conditional probability of D given the complement of F will be 5%. Okay? So this is the Venn diagram for this example. 아시겠죠? 그러니까 F의 25%가 디펙티브 파트고, 그리고 F'의 5%가 디펙티브 파트니까 총 요만큼이 디펙티브 파트가 되는 거예요. And this is another example. And this is the example 2-22. And tab 2-3 shows that 400 parts are classified by surface flows and functionally defective. And in this case, please answer the following two questions. First one is the conditional probability of D given F, right? So the number of D given F will be 10, right? Because D is influenced by the surface flow, and only 10D can be obtained when there is a surface flow. So this is the previous event, and this is the next event. So the number of D given F will be 10. And the probability of D given F can be calculated by dividing this 10 by this 40. Right? So the first question will be the conditional probability of D given F equals to 10 divided by 40, that equals to 0.25. And what about the other question? That is the conditional probability of D given the complement of F. The number of D given the complement of F will be 18, right? So the 18 should be divided by the total number of the case including surface flows, that is 360. So the conditional probability of D given the complement of F equals to 18 divided by 360, and that is equals to 0.05. And to calculate these two equations based on the conditional probability rule, we can use this relationship. The conditional probability of an event B given an event A, denoted as the conditional probability of an event B given event A, equals to this equation. So the complement of the conditional probability of an event B given event A equals to the probability of the intersection of A and B divided by the probability of A. When the probability of A is larger than 0. On a relative frequency perspective, equally likely outcomes can be the probability of A can be calculated by the ratio of the number of outcomes in A divided by the total outcomes. And also, the probability of the intersection of A and B can be calculated by the ratio of number of outcomes in the intersection of A and B and the total outcomes. Consequently, in the case of equally likely outcomes, the conditional probability of an event B and event A will be the ratio of the number of outcomes in the intersection of A and B and the number of outcomes in an event A. Why? Because N is eliminated each other. Okay? So this is the same example with 2-12-2. And we're going to calculate this based on the conditional probability rule. And this is the same table. And we can calculate the first example by this equation. So first we have to calculate the probability of the intersection of A and B, right? In this case, D and F. So the intersection of the D and F will be 10. In this case, the probability of the intersection of A and B will be 10 divided by the total number 400. Okay? And the probability of A, in this case F, there will be 40, right? These are the H, D, and F. Okay? And the probability of F, that equals to 40 divided by 400, right? Because the number of F is 40, right? And we have to divide this 40 by the total number 400 to calculate the probability. Okay? So, based on this equation, the conditional probability of D given F will be 10 divided by 400, 40 divided by 400, right? So the 400 is eliminated. So this will be 10 divided by 40, that equals to 0.25. Okay? And what is the next question? We need to calculate the conditional probability of D given F prime. In this case, we have to calculate the probability of the intersection of D and F prime first. The intersection of D and F prime will be 18, right? So 18 divided by 400. Okay? And the probability of F prime will be 360 divided by 400. So, based on this equation, this conditional probability can be 18 divided by 400, 300 divided by 400, and the 400 can be eliminated. That equals to 18 divided by 360. So there will be 0.05. So based on the conditional probability rule, we can calculate the probability. And also, we can use the tree diagram to calculate the conditional probability. And this is the condition first. At first stage, which is about the surface flow, every original part of the 400 is equally likely. And this is the second question. At second stage, which is about defective, the probability is conditional upon the part in the prior stage. So we are starting with the surface flow, okay? We have two options. First one is that there is no surface flow, and there is a surface flow. And as shown in the first case, this is equally likely. So the probability of there is no surface flow will be 360 divided by 400. So that is 360 divided by 400. And the case there is a surface flow should be 40 divided by 400. Okay? So that will be 40 divided by 400. And this is the first case, first stage. And there is also the second stage. That is the conditional probability. That is the defective. And we also have two options. First one, there is no defective, and there is a defective, right? And also, in the case there is a surface flow, we also can have two defective options. There is no defective, and there is a defective. Okay? But in this case, the probability is conditional upon the part which is about the surface flow in the previous stage. So the probability of that there is no defective when there is no surface flow, there will be there is no defective and there is no surface flow. That is 342 divided by 300. Okay? Because this is the conditional rule. And what is the conditional probability of that there is a defective? when there is no surface flow. There is a defective when there is no surface flow. There will be 18 divided by 360. And what is the conditional probability there is no defective when there is a surface flow? There is no defective when there is surface flow. That is 30, right? So the conditional probability will be 30 divided by this total number 40. Because in this case, there is a surface flow. Okay? And the conditional probability of that there is a defective when there is a surface flow, there will be 10 divided by 40. And this is the tree diagram for the conditional probability. And also, this will be the conditional probability. And now, we are going to discuss about the random samples and the conditional probability. Random normally means each item is equally likely to be chosen. If more than one item is sampled, randomly denotes that every sample outcome is equally likely. 그러니까 랜덤이라고 표현이 되면 각각의 뽑을 확률이 동일하다고 보시면 돼요. 아시겠죠? 그러니까 이미 무작위로 뽑혔다 그러면 뽑힐 확률이 똑같은 경우에서 뽑혔다라고 생각하시면 돼요. This is the example. If two items are taken from this sample, including A, B, C without replacement, the ordered sample space will be AB, AC, BC, ACB, right? And the unordered sample space will be AB, AC, and BC. And it is a type of enumeration which is called 나열 열거 in Korean. But it is too difficult to when we have a large sample space. 그 sample space가 굉장히 커지면은 다 이렇게 나열해서 쓰기가 어렵잖아요. 그죠? So in this case, we normally use the conditional probability to calculate the number of enumeration. And this is another example for the case of sampling without replacement. A day's production of 850 parts contains 50 defectives. And 2 parts are selected randomly without replacement. And what is the probability that the second part is defective given that the first part is defective? This is the conditional probability concept, right? So, based on this question, the first part is already selected, and that is defective. That means we only have 49 defectives and 849 total parts, right? Because we already select the first part and the first part is defective. 그러니까 첫 번째 이미 뽑았고 뽑은 게 defective예요. 그러면 저희가 두 번째 뽑을 수 있는 거는 여기서만 뽑을 수 있을 거 아니에요. 그죠? So in this case, what is the probability that the second part is also defective? There will be 49 divided by 849, right? Okay? So, A equals the event that the first part is defective, and B equals the event that the second part is defective. And this is calculated by the conditional probability of B given A from this equation. If 3 parts are selected randomly, what is the probability that the first 2 parts are defective, while the third is not? In this case, we can select the first part, but the first part should be defective. And the second part should be defective also. And the third part should not be defective. So all these three things are connected as the condition, the end condition, right? So we have to use the multiplication law in this case. So what is the probability to select the first defective part? There will be 50 divided by 850, right? Multiplied by, what is the probability that the second part is defective? There will be, we only have 49 defectives left, and we have 849 parts left, right? Because we already selected the first one. And what is the possibility that the third part is not defective? That will be 800 divided by 848. Okay? So this is the answer for this question. So in this case, we have to use the multiplication law. And the conditional probability definition can be rewritten to provide a formula known as the multiplication rule. And this is the multiplication rule. The probability of the intersection of A and B equals to the conditional probability of D given A multiplied by the probability of A. And this can be also expressed as the conditional probability of A given B multiplied by the probability of B. So in this case, we have to be very careful about the location of the A and B. The last expression is obtained by the interchanging A and B. And this is the example to explain about the multiplication rule. For the machining stages, the probability that a part made in the first stage of a machine operation meets specification is 0.9. And given that the first stage meets specifications, the probability that the second stage meets specifications is 0.95. And this is the conditional probability, right? Because there is a given that the first stage meets specification. So in this case, what is the probability that both stages meet specifications? This means that the first stage should meet the specification and the second stage meet specification, right? So this is connected as end condition, and end condition can be expressed as the intersection, right? Or is the union. End is the intersection. So that will be the probability of the intersection of, I will denote this as A, this as B, A, B, right? And this can be calculated by the conditional probability of B given A multiplied by the probability of A, right? And as I mentioned previously, the second question is the conditional probability, because given that the first stage meets specification, the probability that the second stage misspecification is 0.95. 그러니까 기분이 들어가 있잖아요. 그러니까 이미 주어진 상태에서 이거가 진행이 된 거예요. 그러니까 조건부 확률이라고 보시면 되고요. So 0.95 is the conditional probability of an event B given event A, right? Multiplied by what is the probability of the event A? That is 0.9. So the answer is 0.95 multiplied by 0.9. That equals to 0.855. Okay? And this is another example. 이건 앞에서 제가 A랑 B 한 거 그냥 다시 설명한 거예요. 그럼 넘어갈게요. And this is about the total probability rule, which is called 전확률 공식 in Korean. And in the case of the mutually exclusive subset, A and the complement of A are mutually exclusive. And in that case, the intersection of A and B and the complement of A intersection B are mutually exclusive. And in that case, B equals to the B intersection A union B intersection A prime. And this can be expressed by the Venn diagram. This is the event A, and this is the complement of event A, and there is a subset B here. That is B. And this part will be the intersection of B and A, right? And this part will be the intersection of B and A prime. Okay? So the subset B can be the union of the intersection of B and A and the intersection of B and A prime. Okay? So for any two events, A and B, the probability of B can be calculated based on this equation, based on the total probability rule. And we also express this as this equation in previous slide, right? The intersection of the probability of the intersection of B and A equals to the conditional probability of B given A multiplied by the probability of A, right? And as I mentioned previously, the union can be expressed as plus, right? And the intersection can be expressed as multiplication. So this is another example to explain about the total probability rule here. And what is the probability of failure? And this is the table. The left column indicates the probability of failure. The center column indicates the level of contamination, and the indicates the probability of level. So this is connected with this one, right? And F denotes the event that the product fails, and H denotes the event that the semiconductor is exposed to high contamination during manufacturing. So the question is this, right? And based on the total probability rule, this can be calculated by based on the previous equation here. And based on this equation, this can be rewritten as right? And so, what is the conditional probability of F given H? That is 0.1, right? So, the conditional probability of F H will be 0.1. Okay? Because this is the probability of failure, probability. So, what is the probability of H? That is 0.2, right? So in this case, we don't have to consider about the probability of failure. In this case, we are going to only have two options, high contamination and not high contamination. And the probability of high contamination is 0.2, right? So the probability of H equals to 0.2. And what is the conditional probability of F H prime? There will be 0.005, okay? And what is the probability of the complement of H? There will be 0.8. Okay? So, this will be can be expressed as this equation. And finally, this can be 0.1 multiplied by 0.2 plus 0.005 multiplied by 0.8. Okay? And that equals to 0.02 plus 0.004. That equals to 0.024. Okay? So, based on the total probability rule, we can calculate the probability of failure in this question. And this is the total probability rule for multiple events. If there is E1, E2, blah, 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 and EK, are K mutually exclusive and exhaustive subsets. In this case, the probability of an event B can be calculated by the summation of each the probability of the intersection, okay? And also, each probability of intersection can be expressed by this conditional probability, right? So, we can calculate the probability of an event based on this equation. And that is expressed as the Venn diagram also. This is the sample space. And this is the event 1, event 2, event 3, and this is the event K. And this is the subset B. This will be the intersection of B and E1. This will be the intersection of B and E2. This is the intersection of B and EK, right? So based on this total probability rule, we can calculate the total probability of event of subset B based on the summation of the intersections. Okay? So this is the end of today's class. And have a nice weekend. 수고하셨습니다.